1927, a French aristocrat named Louis de Broglie stood up in front of the most brilliant physicists who have ever been alive at the same time, and he told them he had solved wave-particle duality. Not that he had a promising lead, not that he had an interesting hypothesis worth exploring. He told them the answer: the particle is always a particle. The wave is always a wave. The wave guides the particle. There is no duality. There never was. Einstein had already seen the work 3 years earlier and called it one of the most impressive things he had ever read. Experiments had confirmed its core prediction within months. De Broglie had won, or was about to win, the Nobel Prize for part of the idea. And the solution he presented that day in Brussels was not a sketch or an outline. It was a mathematically complete framework that explained interference, diffraction, and quantization without invoking a single mystery. The particle goes through one slit. The wave goes through both. The wave tells the particle where to land. You get the interference pattern. Done. That solution was rejected, not because someone found a flaw in the math, not because an experiment contradicted it. It was rejected because the wrong people were in the room and the right person was too polite to fight back. Within 2 years, de Broglie had abandoned his own theory. Within 5 years, a mathematician published a proof claiming that what de Broglie proposed was literally impossible. That proof was wrong. A woman named Grete Hermann found the error 3 years later. Nobody listened to her. The proof stood unchallenged for 34 years. And during those 34 years, every physicist on Earth was taught that the question de Broglie had answered was fundamentally unanswerable. That wave-particle duality was a built-in mystery of reality, and anyone who tried to resolve it was either a crank or a fool. You were taught this if you took a physics class at any level in the last 90 years. You were taught that particles sometimes behave like waves and sometimes behave like particles, and that this is simply how the universe works, that there is no deeper explanation, that asking for one is to miss the point of quantum mechanics entirely, and that is not true. It has never been true. The answer has been sitting in the published scientific literature since 1927. It was confirmed, extended, and made fully rigorous in 1952. It produces identical experimental predictions to the version of quantum mechanics you were taught. Every experiment, every measurement, every statistical distribution, the same numbers, and you have almost certainly never heard of it. The question this video is going to try to answer is not what the solution is. I will explain that, and it is simpler than you expect. The real question is darker. If wave-particle duality was solved almost 100 years ago, why is every physicist still taught that it is a mystery? And the answer to that question involves broken mathematical proofs, political persecution, a physicist whose passport was confiscated in Brazil, another who died 1 year before the Nobel Prize he deserved, a family shattered across parallel universes, and a pattern of institutional suppression so thorough that when physicists were surveyed about their preferred interpretation of quantum mechanics in 2013, pilot wave theory, the theory that actually solves the problem, received exactly 0% of the vote. Not a minority position, not a fringe view with 3 supporters. 0. Something about that number should make you deeply uncomfortable, because either the answer is wrong, in which case someone should be able to tell you specifically what is wrong with it and why it fails, or the answer is right, and the most successful scientific community in human history has been quietly ignoring it for almost a century. And if they have been ignoring it, the question you should be asking is not just why, the question is what else has been erased the same way. That is where this is going. But we have a long way to travel before we get there. Louis Victor Pierre Raymond de Broglie was born on August 15, 1892, in Dieppe, France, into a family whose lineage of military and political influence stretched back to the court of Louis XIV. A great-grandfather fought alongside Lafayette in the American Revolution. The de Broglies were not scientists. They were aristocrats, military men, diplomats. Louis's older brother Maurice, the sixth Duc de Broglie, broke the mold by becoming an experimental physicist. Maurice specialized in X-rays and ran a private laboratory in the family mansion in Paris, a detail that gives you a sense of the wealth involved. And it was in conversations with Maurice, always circling back to the same puzzle about X-rays behaving as both waves and particles, that the younger de Broglie had his great insight. The puzzle was fundamental. By the early 1920s, it was clear that light behaved as both a wave and a particle. Einstein had shown in 1905 that light comes in discrete packets called photons, each carrying a specific amount of energy proportional to its frequency. But light also interferes with itself, diffracts around obstacles, and does everything else that waves do. Thomas Young had demonstrated wave-like interference in 1801 with his famous double-slit experiment. Two descriptions of the same phenomenon, both confirmed by experiment, apparently incompatible. 2 centuries of physics, and nobody could reconcile them. De Broglie's insight, which he later said came to him suddenly during the summer of 1923, was elegant in its simplicity. If light, which everyone had assumed was a wave, also behaves as a particle, then maybe matter, which everyone assumed was made of particles, also behaves as a wave. Maybe the so-called duality is not a special property of light. Maybe it is a universal property of everything. He proposed that every particle, every electron, every atom, every object in the universe has an associated wave, and that the wavelength of that wave is given by Planck's constant divided by the particle's momentum. Lambda equals h over p, one equation, and it implied that the quantum world was not fundamentally mysterious. Waves and particles coexist. Both are real. The relationship between them is perfectly clear once you accept that both exist at the same time. He defended this as his doctoral thesis on November 25, 1924, at the University of Paris. The thesis was titled Recherches sur la théorie des quanta, Research on the Theory of Quanta. His committee was skeptical in a way that would be almost comical if the consequences had not been so severe. The physicist Charles Victor Maugin admitted 30 years later that at the time of the defense, he did not believe in the physical reality of waves associated with material particles. Paul Langevin, de Broglie's own supervisor, did not believe in photons. De Broglie recalled Langevin saying during the defense, "Oh, photons, we don't really know if they exist." The man supervising the thesis did not accept one of its foundational premises. But Langevin, to his credit, hedged his bets. He sent a copy to Albert Einstein in Berlin. Einstein's response changed everything. In a letter dated December 16, 1924, Einstein wrote back to Langevin and said that de Broglie had lifted a corner of the Great Veil. According to widely cited accounts, Einstein declared the thesis deserved a Nobel Prize rather than a doctorate. De Broglie later noted with characteristic dry humor that since Langevin had great regard for Einstein, this opinion changed his attitude considerably. Einstein then recommended the work to Erwin Schrödinger in Vienna, who was directly inspired by de Broglie's wave hypothesis to formulate what became the Schrödinger equation, arguably the most important equation in all of quantum mechanics. Schrödinger acknowledged this himself, writing that he had been inspired by de Broglie and by brief yet infinitely far-seeing remarks of Einstein. Experimental confirmation came remarkably fast. In 1927, Clinton Davison and Lester Germer at Bell Labs fired electrons at a nickel crystal and observed a diffraction pattern. The electrons scattered in peaks and valleys, exactly the way waves would diffract from a crystal lattice. The measured wavelength matched de Broglie's formula precisely. George Paget Thomson independently confirmed electron diffraction through thin metal films. De Broglie received the 1929 Nobel Prize in Physics for his discovery of the wave nature of electrons. But here is the part that the Nobel did not recognize, and it is the part that matters for everything that follows. De Broglie did not think the wave was merely a mathematical tool for calculating probabilities, which is what the Copenhagen interpretation would soon turn it into. He believed the wave was physically real, a field propagating through actual space, guiding the particle along a definite trajectory. This was not a vague philosophical preference. It was a specific, mathematically formulated theory. The wave goes everywhere. The particle surfs on it. The particle follows a specific path determined by the gradient of the wave's phase. And in this picture, there is no wave-particle duality at all. The particle is always a particle. The wave is always a wave. Both exist. Both are real. What looks like duality is just two aspects of a single physical system. This is the pilot wave theory, the theory de l'onde pilote, and in October of 1927, de Broglie presented it at the most important gathering of physicists in human history. The 5th Solvay International Conference, convened on October 24, 1927, at the Hotel Metropole in Brussels. It was titled Electrons and Photons and was chaired by Hendrik Lorentz. 29 physicists attended. 17 of them were or would become Nobel laureates. Einstein, Bohr, Heisenberg, Pauli, Dirac, Schrödinger, Born, Planck, Marie Curie, Arthur Compton, de Broglie, all in the same room for 6 days. The famous conference photograph, with all 29 arranged in 3 rows on the hotel steps, is routinely called the most intelligent picture ever taken. Look at it sometime. You will recognize face after face from your physics textbooks. Every one of them was in that room when de Broglie stood up and presented the answer. He presented his pilot wave theory on the conference's 3rd day. He wrote, translating from the French, "One can conceive the corpuscle as guided by the wave which plays the role of pilot wave." The mathematics were clear. The wave function satisfies the Schrödinger equation. The particle follows the wave along a trajectory given by the gradient of the wave function's phase divided by the mass. Contrary to what was claimed for decades afterward, scholars Guido Bacialupi and Anthony Valentini showed in their meticulous 2009 reconstruction of the conference proceedings, published as Quantum Theory at the Crossroads, that de Broglie's version already handled multiple particles, not just a single one. This was not a half-formed idea offered tentatively to a room of skeptics. It was a functioning theory. Wolfgang Pauli destroyed it, or appeared to. Pauli argued that pilot wave theory could not properly handle inelastic scattering, a specific technical problem involving energy transfer between particles during collisions. Baciagalupi and Valentini found, after detailed analysis of the original notes, that de Broglie actually gave the correct technical rebuttal. The specific technique Pauli cited, one developed by Enrico Fermi, could not be generalized to the many-body case in the way Pauli claimed. But de Broglie was mild-mannered and aristocratic. He did not push back forcefully. Pauli was brilliant, savage, and feared. The audience, filled with Pauli's allies and admirers, walked away with the impression that the objection stood. The Stanford Encyclopedia of Philosophy puts it bluntly, noting that de Broglie responded very poorly and no doubt made a rather bad impression on the illustrious audience. Meanwhile, Bohr and Heisenberg delivered what amounted to a manifesto for the Copenhagen interpretation. They declared, from the conference proceedings, "We consider quantum mechanics to be a closed theory whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. Closed, finished, complete, not open to alternatives or revisions." Heisenberg later called the conference the event where quantum theory was officially completed. Paul Langevin, who was present and who had supervised de Broglie's thesis, disagreed. He called it the conference where the confusion of ideas reached its peak. Einstein attended but did not specifically defend de Broglie's pilot wave. He was fighting his own battle against quantum indeterminacy, the beginning of the legendary Bohr-Einstein debates. Einstein challenged Bohr at dinner, in the hallways, on walks through Brussels. But he did not champion pilot wave theory specifically. De Broglie fought alone, and alone against Pauli and Born and Heisenberg and the institutional weight of the Copenhagen school. He lost. By 1928, de Broglie had abandoned his own theory. He later wrote about this decision with painful honesty that still reverberates almost a century later. Discouraged by the rather unfavorable reception accorded my ideas by most theoretical physicists, who were strongly attracted by the formal elegance and apparent rigor of the purely probabilistic interpretation, I too came round to that interpretation, and for more than 20 years admitted its correctness. Think about what he is saying. The man who solved wave-particle duality gave up on his own answer because the room was hostile, not because anyone proved him wrong, because the crowd was against him, and the crowd was famous. But the rejection at Solvay was only the beginning. The Copenhagen school needed to make sure the door stayed closed, and the tool they used to lock it was a mathematical proof, a proof published by one of the most brilliant mathematicians of the 20th century, a proof that was wrong from the day it was written. And the story of that proof and of the woman who saw through it and was ignored is where this gets genuinely ugly. In 1932, John von Neumann, a Hungarian-American mathematician whose contributions span set theory, functional analysis, game theory, computer science, and nuclear weapons design, published a monumental book called Mathematical Foundations of Quantum Mechanics. Von Neumann was not merely smart. He was considered by many of his contemporaries to be the most formidable intellect of the century. When von Neumann declared something mathematically proven, the scientific world accepted it without question. And what he declared in chapter 4 of his book was that no theory of hidden variables, no theory in which particles have definite properties at all times, could ever reproduce the predictions of quantum mechanics. Not that it was difficult to do, not that it was unlikely to succeed, mathematically impossible. His conclusion was absolute. Translated from the German, he wrote, "It is therefore not a question of a reinterpretation of quantum mechanics. The present system would have to be objectively false in order that another description than the statistical one be possible." In other words, unless quantum mechanics itself was wrong, there could be no underlying deterministic theory, no pilot waves, no particle trajectories, no hidden variables of any kind. The impact on physics was immediate and lasting. Von Neumann's proof became what physicists later described as gospel. It was cited reverently, invoked as a final authority, and examined almost never. Max Born wrote confidently in 1949 that no concealed parameters can be introduced, with the help of which the indeterministic description could be transformed into a deterministic one. The matter was settled. The greatest mathematician alive had proven it mathematically. End of discussion. But the proof rested on an assumption that was physically absurd. Von Neumann assumed that a property called linearity of expectation values must hold not only for quantum mechanical states, where it is uncontroversial, but also for hypothetical hidden variable states, where it is completely unjustified. In concrete terms, imagine you have two measurements that cannot be performed simultaneously, say the position and the momentum of a particle. Quantum mechanics says that if you measure the sum of these two quantities, the average result over many trials equals the sum of the individual averages. Von Neumann assumed this must also be true for hidden variable states, for the hypothetical underlying reality where the particle has definite values. But these measurements require different, mutually exclusive experimental setups. You cannot measure position and momentum at the same time. There is no physical apparatus that does both simultaneously. So demanding that the hidden variable state respect linearity across incompatible experiments is demanding something that has no physical basis. Von Neumann assumed the conclusion he was trying to prove. A woman saw this immediately. In 1935, 3 years after von Neumann's book was published, a German mathematician and philosopher named Grete Hermann published a paper in the Journal of the Frisian School of Philosophy. Hermann had studied under Emmy Noether, one of the greatest mathematicians in history, and she was rigorous and precise. Her paper, titled "The Natural Philosophical Foundations of Quantum Mechanics," identified the exact flaw in von Neumann's reasoning. She pointed out that his key assumption was not physically justified, and that the proof therefore failed to rule out the theories it claimed to rule out. She was completely ignored, not argued against, not debated, ignored. She sent a copy of her paper to Paul Dirac. It was found in his archive decades later, apparently unread. The physicist David Bohm noted in 1993 that a few years after von Neumann's proof, Grete Hermann had pointed out a glaring deficiency in the argument, but she seems to have been entirely ignored. The physics community did not engage with her work because she published in a philosophy journal, because she was a woman working during the rise of Nazism in Germany, and because nobody wanted to hear that the great von Neumann had made a mistake. The combination of institutional prestige and casual sexism meant that a correct and devastating critique of the most influential proof in the foundations of physics sat unread for more than 3 decades. From 1932 to 1966, von Neumann's broken proof shaped the entire culture of physics. 34 years. During those years, it was cited in every major textbook as the definitive mathematical demonstration. that hidden variable theories were impossible. An entire generation of physicists was trained to believe that even asking de Broglie's question, let alone answering it, was mathematically prohibited. The culture of shut up and calculate that defined mid-century physics was built on this foundation, and the foundation was cracked. That phrase, shut up and calculate, you have probably heard it attributed to Richard Feynman. It was not Feynman. It was coined by the Cornell physicist N. David Bohm in his April 1989 column for Physics Today. He wrote it to capture the culture of his graduate school days at Harvard in the late 1950s. His professors warned him he would never get a PhD if he allowed himself to be distracted by frivolities like the meaning of quantum mechanics. Get back to serious business and produce some results. By 2004, Merman said he was not proud of the phrase. He called it snide and mindlessly dismissive. But by then, the damage was thorough. 2 full generations of physicists had been trained to believe that asking what is actually happening in quantum mechanics was not a legitimate scientific question. And behind the proof stood a far more effective instrument of suppression: the textbook pipeline. Niels Bohr ran the most influential physics institute in the world in Copenhagen. Werner Heisenberg traveled the globe, giving lectures promoting what he explicitly called the Copenhagen spirit of quantum theory. Their students, nurtured in the Copenhagen doctrine, dispersed to universities worldwide, many of them fleeing Hitler in the 1930s. They carried the orthodoxy with them. Wolfgang Pauli served as enforcer, demolishing critics with a combination of brilliance and cruelty that made other physicists afraid to speak up. The canonical textbooks cemented everything. Dirac's Principles of Quantum Mechanics, 1930, Heisenberg's 1930 Chicago Lectures, Landau and Lifshitz's Quantum Mechanics, 1958. None of them mention pilot wave theory, not as a refuted alternative, not as a historical curiosity. It is simply not there. And after a generation of physicists learned from these books, the absence became self-reinforcing. Nobody learned it, so nobody taught it. Nobody taught it, so nobody worked on it. Nobody worked on it, so nobody learned it. The erasure perpetuated itself without anyone needing to actively maintain it. This is the thing that should disturb you more than any broken proof or any conference debate. Not the open rejection, the quiet omission, the way an idea can be removed from a scientific discipline, not by refutation, but by silence. And the silence lasted for 25 years, until a man in exile, stripped of his citizenship, fired from his job, driven from his country by a combination of McCarthyism and scientific establishment hostility, sat down in Sao Paulo and proved the impossible. David Joseph Bohm was born on December 20th, 1917, in Wilkes-Barre, Pennsylvania. It is a coal mining town. His father, Samuel, was a Hungarian Jewish immigrant who ran a furniture store. His mother, Frida, suffered from mental instability that worsened throughout Bohm's childhood. He grew up in modest circumstances that could not have been more different from de Broglie's aristocratic Parisian upbringing. He was brilliant from the start, the kind of student who understood things by rebuilding them from the ground up, rather than memorizing what he was told. He earned his bachelor's degree at Pennsylvania State College in 1939, spent a miserable year at Caltech, where he did not connect with the faculty, and then transferred to UC Berkeley to study under J. Robert Oppenheimer, who was at the time the most charismatic and influential theoretical physicist in America. Bohm's PhD thesis on proton-deuteron scattering was classified for the Manhattan Project. Here is the absurdity of Bohm's early career. His own doctoral thesis was classified. He could not access his own work. And the reason he could not access it was that he had been denied the security clearance required to participate in the Manhattan Project, despite the fact that his research was considered important enough to be classified. Oppenheimer personally certified the thesis, so Bohm could graduate. At Princeton University, where Bohm became an assistant professor in 1947, he took a room next door to Albert Einstein. The two became close friends. They met regularly, sometimes daily, to discuss physics and philosophy in Einstein's office at the Institute for Advanced Study. Einstein called Bohm his spiritual son. The relationship was formative in both directions. Einstein valued Bohm's willingness to take foundational questions seriously. Bohm valued Einstein's conviction that quantum mechanics in its Copenhagen form was incomplete. In 1951, Bohm published a textbook called Quantum Theory. It was immediately recognized as the clearest and most pedagogically effective exposition of the Copenhagen interpretation that had ever been written. Even Niels Bohr praised it. The irony of what happened next is almost unbearable. Bohm wrote the definitive book on the interpretation of quantum mechanics that he was about to overturn. He gave a copy to Einstein. In the conversations that followed, Einstein methodically convinced Bohm that something was fundamentally wrong with the Copenhagen picture. It was in the process of writing the textbook, in having to state the Copenhagen interpretation with total clarity and precision, that Bohm realized how many unresolved problems it contained. The measurement problem, the arbitrary division between observer and system, the mysterious collapse of the wave function. Writing the book showed him every crack in the foundation, and Einstein helped him see that the cracks were not cosmetic, they were structural. Then the United States government destroyed his career. Bohm had joined the Communist Party at Berkeley in 1942. He quit after roughly 9 months, finding the meetings, in his own words, petty and exhausting. He helped organize a union at the Radiation Laboratory. This was enough. On April 21, 1949, a subpoena from the House Un-American Activities Committee arrived at his office in Palmer Physical Laboratory at Princeton. Bohm pleaded the Fifth Amendment and refused to name colleagues. On December 4, 1950, he was indicted for contempt of Congress. Princeton immediately suspended him. He was forbidden from setting foot on campus. In May of 1951, Bohm was acquitted. It did not matter. Princeton's president Harold Dodds refused to reinstate him, writing that Bohm lacked those qualities of personality and judgment which should be expected of a member of its faculty. This from a man who had never questioned Bohm's physics. And then came the betrayal that cut deepest. Oppenheimer, his former mentor and PhD supervisor, the man who had certified his classified thesis, was called to give testimony about Bohm. Oppenheimer, under pressure from security services, was willing to name names. He called Bohm politically suspect and possibly dangerous. This was not an honest assessment. Oppenheimer knew Bohm had left the party after 9 months, years earlier, and had found it tedious. He threw his former student to the wolves to protect his own increasingly precarious position. And Bohm learned about it only later, after the damage was done. Bohm left the United States in the autumn of 1951, accepting a position at the University of São Paulo in Brazil. At the American consulate in São Paulo, his passport was confiscated. He was stateless. a brilliant physicist at the peak of his intellectual powers, cut off from the country of his birth, separated from Einstein and the Princeton community that had nourished his thinking, stripped of his institutional standing. And it was there, in that exile, in that isolation, that he wrote the two papers that should have changed everything. A suggested interpretation of the quantum theory in terms of hidden variables, parts 1 and 2, appeared in Physical Review, volume 85, number 2, pages 166 through 193, published on January 15th, 1952. Part 2 was received by the journal on July 5th, 1951, meaning Bohm was working on this in the immediate aftermath of his Hugh testimony, his indictment, and his exile. Think about the conditions under which this work was produced, not in a prestigious institute surrounded by brilliant colleagues. In exile, under political persecution, alone. What Bohm proposed was a complete, deterministic reformulation of quantum mechanics. Every particle has a definite position at all times. The wave function is a real physical field that guides the particle's motion. The particle moves according to a guiding equation, which says that its velocity is the gradient of the wave function's phase divided by the particle's mass. If you write the wave function as an amplitude times a complex exponential, the particle simply follows the gradient of the phase. It is a modification of the classical Hamilton-Jacobi equation from mechanics with one additional term. That additional term is the quantum potential, and the quantum potential is what makes everything work. Ohm defined it as Q equals negative h bar squared over 2m times the Laplacian of r divided by r, where r is the amplitude of the wave function. This quantity has a property that is unlike anything in classical physics. It depends on the shape of the wave function, not on its intensity. A wave function with very small amplitude, far from any source, can exert the same guiding influence as a wave function with enormous amplitude nearby. The quantum potential is about form, not strength. It carries information about the global structure of the entire experimental setup, including parts of the apparatus that the particle itself will never encounter directly. This is how Bohm's theory handles the double slit. The wave goes through both slits, the particle goes through one. At the quantum potential, which depends on the shape of the full wave function, including the part that went through the other slit, steers the particle into the interference pattern. The particle does not need to know about both slits. The quantum potential knows, and the particle follows. Let me slow down here because this deserves more than a quick summary. What Bohm showed is that the interference pattern in the double-slit experiment is not a mystery at all. It is a consequence of the quantum potential's shape. When both slits are open, the wave function on the far side of the barrier has a complex interference structure, peaks and valleys, bright bands and dark bands. The quantum potential inherits this structure. It creates a landscape of hills and valleys that the particle must navigate. The particle is pushed toward the constructive interference regions and away from the destructive interference regions. If you block one slit, the wave function changes shape, the quantum potential changes shape, and the particle's trajectory changes accordingly. The interference pattern disappears, not because the particle somehow knew it could go through both slits, but because the wave that was guiding it no longer has the interference structure. There is nothing mystical happening. There is a wave and a particle and a force between them. And the trajectories themselves have a beautiful and specific structure that was later confirmed by experiment. In the Bohmian picture, the particle trajectories in a double-slit experiment never cross the axis of symmetry between the two slits. A particle that enters through the upper slit always lands on the upper half of the detection screen. A particle that enters through the lower slit always lands on the lower half. The trajectories curve, weave, and bunch together in the bright bands, but they never cross the midline. This is a specific, testable prediction that distinguishes Bohmian mechanics from any naive. The particle goes through both slits. Picture. And in 2011, as I will describe later, this exact trajectory structure was measured experimentally with real photons. Think about what this means for everything you were taught about the double-slit experiment. You were taught that the experiment reveals something deeply strange about reality, that the particle somehow interferes with itself, that it goes through both slits simultaneously, that asking which slit it went through destroys the pattern. In Bohm's theory, none of that is strange. The particle goes through one slit. The wave goes through both. The wave creates the interference. The particle follows the wave. If you put a detector at one slit to see which slit the particle goes through, you change the wave function. You change the quantum potential. You change the trajectories. The pattern disappears because you have physically altered the guiding field, not because you have philosophically observed something. The mystery was never in the physics. The mystery was in the interpretation, and the interpretation was chosen by committee vote in 1927. Bohm used a vivid analogy. Imagine a ship guided by radio signals. The ship's energy comes from its own engines, but the information that determines its course comes from the radar wave, and the strength of that radar signal is irrelevant. What matters is the form of the signal, the information it carries about the ship's surroundings. The quantum potential works the same way. It carries information about the shape of reality, and its influence does not diminish with distance. This is what makes the theory explicitly non-local. In a two-particle system, the quantum potential for one particle depends on the position of the other particle, no matter how far apart they are. Change the configuration here, and the guidance there responds instantaneously. And here is the critical fact, the one that von Neumann's proof was supposed to make impossible. Bohm's theory produces identical predictions to standard quantum mechanics. Every experiment that standard quantum mechanics correctly predicts, Bohm's theory correctly predicts. The statistical distributions are the same. The measurement outcomes are the same. The correlations are the same. This is not an approximation. This is not a rough agreement. It is mathematical equivalence, proven in the 1952 papers. The very existence of Bohm's theory was a living refutation of von Neumann's impossibility proof. Bohm had built the thing that von Neumann said could not be built. And unlike de Broglie's 1927 version, Bohm's formulation handled measurement explicitly. It resolved the measurement problem without wave function collapse. What appears as collapse in the standard picture is, in Bohm's theory, an effective phenomenon. During a measurement, the wave function branches in configuration space. The particle's actual position selects one branch, and the other branches become dynamically irrelevant through a process now called decoherence. The observer is not special. Measurement is not special. It is just another physical interaction. The physics community's response to these papers reveals something deeply uncomfortable about how science works when institutional power is at stake. Oppenheimer, who is now at the Institute for Advanced Study at Princeton, convened a meeting specifically to find a flaw in Bohm's papers. After several hours of discussion, no flaw was found. According to F. David Pete's 1997 biography, Infinite Potential, Oppenheimer then said, "If we cannot disprove Bohm, then we must agree to ignore him." He called the work juvenile deviationism, a Stalinist political term, a choice of language that is breathtakingly cruel, given that Bohm was already in exile because of alleged communist sympathies. The man who betrayed Bohm to the security services was now organizing a professional boycott of his physics. Niels Bohr called Bohm very foolish. Leon Rosenfeld, who served as Bohr's intellectual enforcer throughout this period, wrote on May 30th, 1952, that the theory was very ingenious but basically wrong, without explaining what specifically was wrong with it. Wolfgang Pauli, in a letter dated December 3rd, 1951, conceded that he could find, and this is a direct translation, no longer the possibility of any logical contradiction in Bohm's work. But he dismissed the theory's additional structure as a check which cannot be cashed. The most honest assessment came wrapped in an insult. Pauli admitted the theory was logically consistent, but declared it valueless anyway. Even Einstein, who was Bohm's closest intellectual ally and who had spent years arguing that quantum mechanics was incomplete, was unenthusiastic about the specific theory Bohm had constructed. In a letter to Max Born, dated May 12, 1952, Einstein wrote, "Have you noticed that Bohm believes he is able to interpret the quantum theory in deterministic terms? That way seems too cheap to me." Einstein wanted a deeper revolution, a wholesale reconstruction of physics. Bohm had provided something more conservative, a reinterpretation that preserved the mathematical structure of quantum mechanics while providing a clear physical picture. Einstein found this aesthetically unsatisfying. He particularly disliked that the wave function lived in abstract configuration space, a mathematical space with 3 dimensions for every particle in the universe, rather than in ordinary 3-dimensional physical space. John Bell, who would later become the theory's most eloquent champion, captured the absurdity of the reception perfectly. He said, "For 25 years, people were saying that hidden variable theories were impossible. After Bohm did it, some of the same people said that now it was trivial. They did a fantastic somersault. First it was impossible. Then, when someone did it, it was dismissed as unimportant. The intellectual dishonesty of this sequence is staggering when you lay it out plainly. The physics community said, hidden variables cannot be done. Bohm did it. The physics community then said, what Bohm did was not worth doing. At no point was it taken seriously. At no point was it engaged with on its actual scientific merits. The response was not, here is the flaw in your theory. The response was, we have agreed not to look at your theory. And this was not a quiet, informal consensus. It was organized. Oppenheimer held meetings to discuss how to respond. Rosenfeld wrote letters coordinating opposition. The word spread through the small, tightly connected world of theoretical physics that Bohm's work was not to be taken seriously. Young physicists who showed interest were warned off. The career incentives were clear. If you wanted a job, a grant, a publication, a place at the table, you did not work on Bohm's theory. You did not cite Bohm's theory. You did not teach Bohm's theory. You shut up and calculated. Bohm's exile continued and deepened. He obtained Brazilian citizenship in 1954, moved to Israel in January 1955 to join the Technion in Haifa, where he married Sarah Wolfson in 1956, then to the University of Bristol in 1957, then to Birkbeck College at the University of London in 1961, where he would spend the rest of his career. At Bristol, with his graduate student Yakir Haranov, he made another major contribution, predicting the Aharonov-Bohm effect, which showed that electromagnetic potentials, not just fields, have direct physical consequences. Charged particles can be affected by electromagnetic potentials in regions where there is zero electromagnetic field. This prediction was experimentally confirmed by Akira Tonomura in 1986 and is now considered one of the most significant results in modern physics. Bohm was not a crank on the margins. He was a physicist of the highest caliber who kept producing important work despite being systematically marginalized. But his pilot wave theory was treated as though it did not exist. Not wrong, not refuted, not debated. Absent from textbooks, absent from conferences, a complete, rigorous, experimentally equivalent formulation of quantum mechanics, published in the most prestigious physics journal in the world. And the professional response was not criticism, but silence. The organized, institutional, comprehensive silence of a community that had decided, as Oppenheimer put it, to agree to ignore him. And here is where the story shifts from being about one theory to being about something larger. Because if what happened to Bohm was a scientific process, if his theory was evaluated on its merits and found wanting, that would be one thing. But that is not what happened. His theory was evaluated politically. It was judged by who proposed it, not by what it said. It was dismissed by people who admitted they could find no logical flaw in it. It was buried by a combination of McCarthyism from the American government and institutional hostility from the physics establishment. The selection of the Copenhagen interpretation as the standard framework of quantum mechanics was not a scientific decision. It was a political one, made by a handful of extraordinarily influential men, enforced by a broken proof, maintained by textbook selection and career incentives, and sustained by the quiet, grinding, effective mechanism of simply never mentioning the alternative. And if that is true, if the foundational framework of the most successful physical theory in history was selected by sociology rather than by evidence, then you need to ask yourself a very uncomfortable question. What else has been selected the same way? What other answers are sitting in journals, published and verified, and quietly ignored because the institutions that decide what counts as physics decided those answers were inconvenient? That question is not rhetorical. And we are not done, because there was one person who asked it, a working-class kid from Belfast who read about von Neumann's proof, believed it, and then saw a man in exile do the thing the proof said was impossible. John Stuart Bell was born on July 28, 1928, in Belfast, Northern Ireland. His family was working class in a way that the phrase does not quite capture. His father traded horses for a living. His mother was a dressmaker. When Bell was accepted to university, his mother sewed his academic gown from blackout curtains left over from the war. He was the first person in his family to attend secondary school, let alone university. He earned first-class honors degrees in both experimental and mathematical physics at Queen's University, Belfast, completed his PhD at the University of Birmingham under the nuclear physicist Rudolf Peierls in 1956, and in 1960 moved with his wife Mary Ross, who was also a physicist, to CERN in Geneva, where he worked on particle accelerator design for the remainder of his career. Quantum foundations was his hobby. That is how he described it. He worked on it evenings, weekends, and during sabbaticals. The work that would eventually reshape the foundations of physics and inspire a Nobel Prize was done in the margins of a career focused on practical particle physics. And the story of how he came to do that work begins with a textbook he read as a student. Bell encountered the hidden variable question as a young man. He read Max Born's book, Natural Philosophy of Cause and Chance, which cited von Neumann's proof that hidden variable theories were mathematically impossible. Bell later recalled that he accepted this and relegated the question to the back of his mind. He got on with more practical things. The proof said it was impossible. Von Neumann said so. Case closed. Then, in 1952, he saw the impossible done. It was in papers by David Bohm, Bell said later. Bohm showed explicitly how parameters could indeed be introduced in terms of which events in quantum mechanics acquire a causal description. The experience was transformative, not just because of the determinism, though that struck Bell as important. What changed Bell's thinking permanently was the elimination of the measurement problem. Bohm's theory did not require a vague, unexplained division of the world into a quantum system and a classical observer. It did not require wave function collapse. Everything was described by the same physics. The particle had a position. The wave function guided it. Measurement was just another physical process. Bell asked himself a question that would consume him for the next 4 decades. He noticed that Bohm's theory had a curious feature. It was explicitly non-local. In a system of 2 entangled particles, the motion of particle 1 depends instantaneously on the position of particle 2, no matter how far apart they are. This is built into the guiding equation. The wave function for 2 particles lives in 6-dimensional configuration space, 3 dimensions for each particle, and the velocity of either particle depends on the full configuration, which includes the other particle's position. There is no getting around this. The non-locality is structural. Bell wanted to know whether this was a quirk of Bohm's specific formulation or something deeper. Could you build a hidden variable theory that was local, one where distant events could not affect each other instantaneously? He spent years thinking about this. During a sabbatical in 1963, which took him to Stanford, Wisconsin, and Brandeis, he finally had the uninterrupted time to work through the mathematics. The result was a paper titled On the Einstein-Podolsky-Rosen Paradox, published in the short-lived journal Physics Physique, Physica, Volume 1, page 195, received November 4th, 1964. The paper is 6 pages long. It may be the most consequential 6 pages in 20th century physics. What Bell proved is this. He showed that any theory in which measurement outcomes are determined by pre-existing local properties, any theory where particles carry their values with them, and where influences do not travel faster than light, must satisfy a certain mathematical constraint. This constraint is called Bell's inequality. He then showed that quantum mechanics predicts situations where Bell's inequality is violated. The predictions of quantum mechanics and the predictions of any local hidden variable theory are different. They disagree, and they disagree in a way that can be tested experimentally. This is crucial, so let me be precise about what it means and what it does not mean. Bell's theorem does not rule out hidden variable theories in general. It rules out local hidden variable theories, theories where the hidden variables are local, meaning they do not communicate faster than light. Bohm's theory is a hidden variable theory, but it is non-local. The quantum potential connects distant particles instantaneously. Bell's theorem does not touch it. Bell's theorem was inspired by Bohm's theory, not aimed at it. And this is where you need to update your mental model if you have been taught otherwise. You may have heard from a physics teacher, from a YouTube video, from a textbook that Bell's theorem proves hidden variables are impossible. That is wrong. It proves that local hidden variables are impossible. The distinction matters enormously, because what Bell actually showed is that reality itself is non-local. Not just Bohm's theory, reality. If quantum mechanics is correct, and every experiment ever performed says it is, then the universe does not respect locality. What happens here can instantaneously affect what happens there, not through any signal, not through any force, through the structure of reality itself. The experiments confirmed it. In 1972, John Clauser and Stuart Friedman at UC Berkeley performed the first experimental test of Bell's inequality using entangled photons produced by a calcium cascade source. They measured the polarization correlations at different angles. The results violated Bell's inequality by more than 5 standard deviations. Quantum mechanics was right. Local hidden variables were dead. But there was a loophole. In Clauser's experiment, the polarizer settings were fixed before the photons were emitted. Maybe, some argued, the photons somehow knew in advance what settings would be used and coordinated their behavior accordingly. This is called the locality loophole. To close it, you would need to change the measurement settings while the photons were already in flight, too fast for any signal traveling at light speed to carry the information from one detector to the other. Alain Aspect, a young French physicist at the University of Paris-Sud, did exactly this in 1982. He used acousto-optical switches that redirected each photon to one of 2 differently oriented polarizers, and the switching happened while the photons were mid-flight. The separation was large enough that no light speed signal could connect one measurement choice to the other. The Bell inequality was still violated. The locality loophole was partially closed. The definitive tests came in 2015, when 3 independent groups closed all major loopholes simultaneously. Ronald Hansen's team at Delft University of Technology used entangled electrons separated by 1.3 kilometers. Anton Zeilinger's group in Vienna used entangled photons with measurement choices determined by cosmic randomness. Photons from distant quasars that had been traveling for billions of years. A NIST team led by Sai-Wu Nam used high-efficiency superconducting photon detectors. All 3 experiments violated Bell's inequality decisively. Every escape route was sealed. The result was as definitive as experimental physics gets. Nature is non-local. The universe does not work locally. Bell was right. Bell did something else during these decades that has been underappreciated. He went back and looked at von Neumann's impossibility proof, the proof that had kept hidden variable theories in the grave for 34 years. In a paper written in 1964, but not published until 1966, because the manuscript was literally misfiled in a drawer at the editorial offices of Reviews of Modern Physics, and lost for over a year, Bell demonstrated the same flaw that Grete Hermann had identified in 1935. Von Neumann's key assumption was physically unjustified. The proof was broken. Bell's assessment of von Neumann, delivered in a 1988 interview with Omni magazine, was devastating. He said the proof of von Neumann is not merely false, but foolish. Not just wrong, foolish. From one of the most careful and precise physicists of his generation, that word carries extraordinary weight. But Bell's frustration extended far beyond one flawed proof. He was angry about the entire culture that the proof had enabled. In a 1982 essay called On the Impossible Pilot Wave, published in Foundations of Physics, Bell asked questions that should keep every physicist awake at night. Why had Bohr not told him about the pilot wave, if only to point out what was wrong with it? Why did von Neumann not consider it? More extraordinarily, why did people go on producing impossibility proofs after Bohm had shown it was possible, as recently as 1978? Why is the pilot wave picture ignored in textbooks? Should it not be taught, not as the only way, but as an antidote to the prevailing complacency, to show that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice? That last phrase, deliberate theoretical choice, it is the most important sentence in the history of quantum foundations, and it has still not been absorbed by the profession that Bell was addressing. Bell spent his final decade arguing passionately for clarity in the foundations. He coined the satirical acronym FAPP, meaning for all practical purposes, to mock Copenhagen's tendency to dismiss deep questions by arguing that the standard formulation works well enough for practical calculations. He proposed the concept of beables, things that actually exist whether anyone observes them or not, as a replacement for the slippery language of observables and measurements. In his 1990 essay, Against Measurement, published in Physics World, Bell argued that words like measurement, system, apparatus, and observable should be banished from the formulation of fundamental physics because they are too vague to bear the weight placed on them. These words, he argued, smuggle in assumptions about where the boundary lies between the quantum world and the classical world, between the thing being observed and the thing doing the observing. And that boundary is never defined. It cannot be defined. It is the central unsolved problem of the Copenhagen interpretation, dressed up in language that makes it look like a feature rather than a bug. On October 1st, 1990, John Bell died of a sudden cerebral hemorrhage at the age of 62. He had been nominated for the Nobel Prize that very year. He did not know this. The Nobel is never awarded posthumously. 32 years later, in 2002, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work on Bell's inequalities. At the Nobel ceremony, Aspect said that the recognition should go first to the late John Stuart Bell. It was gracious. It was also 32 years too late. But Bell's work did more than vindicate Bohm and embarrass von Neumann. It revealed something about the fabric of reality that the Copenhagen interpretation had been specifically designed to avoid confronting. The universe is non-local. What happens here can instantaneously affect what happens there, not through any signal that travels through space, not through any force that diminishes with distance, through the structure of reality itself. In Bohm's theory, this non-locality is explicit and visible in the equations. The quantum potential for a two-particle system depends on the positions of both particles simultaneously, regardless of how far apart they are. Change the configuration of an apparatus on one side of the galaxy, and the quantum potential felt by a particle on the other side changes instantaneously. Bohm used a vivid analogy to explain this. A ship, guided by radar signals, gets its energy from its own engines. The ship moves under its own power, but the information that determines its course comes from the radar wave, and the strength of that radar signal is irrelevant. What matters is the form of the signal, the information it carries about the environment. The quantum potential works the same way. It carries information about the shape of reality, about the form of the wave function, and its influence does not diminish with distance. The implications of this go far beyond any particular experiment. If the universe is non-local in this way, then the universe is not a collection of separate objects scattered through space, each doing its own thing and occasionally interacting through local forces. It is one undivided thing. The wave function for the entire universe is a single entity that encompasses every particle, every interaction, every measurement. It does not care about the distance between things. It connects everything to everything else. When two particles have interacted in the past and then separated to opposite ends of the cosmos, they remain connected through this universal wave function. The quantum potential for one still depends on the position of the other. They are not separate. They never were separate. Separation is an illusion created by looking at the particles in three-dimensional space instead of in the configuration space where the wave function lives. This quality of the universe, this indivisible wholeness, is what Bohm himself spent the last decades of his life thinking about. He called it the implicate order, a reality in which what appears separate and disconnected at the surface is actually folded together at a deeper level. It is not quite right to say the universe has agency, because agency implies choice and the equations are deterministic. But the mathematics describe something that acts as if it remembers. The wave function encodes the entire history of every interaction. It carries that history forward in time, shaping the motion of every particle through the quantum potential. When you set up a double slit experiment, the wave function knows about both slits because it passes through both. When you close one slit, the wave function changes shape and the particle's trajectory changes accordingly. The universe in this picture is not a passive stage. It is the thing that is doing the guiding, and it guides non-locally, instantaneously, across arbitrary distances, without caring about the speed of light or the size of the separation. And the framework that denied this for almost a century, the framework that insisted quantum mechanics was about probabilities and measurements and observer-dependent realities, did so not because the evidence pointed that way, but because the alternative was too unsettling. Non-locality was the thing the Copenhagen architects wanted to avoid. Einstein called it spooky action at a distance and spent decades trying to prove it did not exist. The Copenhagen interpretation was, in part, a strategy for sidestepping the implications of non-locality by declaring that particles do not have definite properties until they are measured, thereby avoiding the question of how those properties could be correlated across vast distances. Bohm's theory refuses to sidestep. It says yes, the universe is non-local. Yes, distant particles are connected. Yes, the wave function is real and it reaches everywhere, and the experiments confirm it. Meanwhile, in a laboratory in Paris, a physicist was accidentally making the invisible visible. In 2005, a student in Yves Couder's laboratory at the University of Paris Diderot made an accidental discovery. A tiny silicone oil droplet, about 0.7 of a millimeter across, placed on a vibrating bath of the same oil, would bounce indefinitely instead of being absorbed. Couder, who was born in 1941 and spent his career studying fluid dynamics, immediately recognized what he was seeing. Each bounce generated a capillary wave on the surface of the oil bath at the Faraday wavelength, approximately 4.75 millimeters. These waves persisted between bounces, and the droplet, instead of bouncing in place, began to surf on the slope of its own wave field. It became a self-propelled walker, a particle being guided by a wave, a pilot wave system, macroscopic, classical, visible to the naked eye. Koda and his collaborator Emmanuel Fort published their first results in Nature in 2005. Then, in 2006, they published a landmark paper in Physical Review Letters. They sent 75 walking droplets through a double slit barrier, one at a time. Each droplet went through one slit. Its wave went through both. And when they compiled a histogram of the scattering angles, they saw a pattern of stripes, not identical to the quantum double slit pattern, but strikingly reminiscent of it. The statistical distribution of where the droplets ended up resembled a diffraction pattern. The analogy reached further than the double slit. In 2009, Eddy, Fort, Moisey, and Kuda published in Physical Review Letters a demonstration of quantum-like tunneling. Walking droplets hitting submerged barriers would sometimes pass through and sometimes bounce back. The outcome was individually unpredictable, but the crossing probability decreased exponentially with barrier thickness, exactly the signature of quantum tunneling. In 2010, Fort, Eddy, Boudaud, Mokhtar, and Kuda, published in the Proceedings of the National Academy of Sciences, showed that walkers subjected to a rotating frame adopted only discrete orbital radii, quantized orbits in a classical system. The constraints came from the dynamic interaction between the droplet and its pilot wave field. In 2012, Eddy and colleagues demonstrated Zeeman-like level splitting, where co-rotating and counter-rotating orbital modes split proportionally to the rotation rate, directly analogous to atomic energy levels splitting in a magnetic field. John W.M. Bush, a professor of applied mathematics at MIT, built a major research program around these walking droplets. Beginning around 2010, his group developed rigorous mathematical models, showed that droplets in a circular corral produce statistical distributions similar to quantum corrals, and taught an entire MIT course on hydrodynamic quantum analogues as recently as the spring of 2024. Then came the challenge, and the person who delivered it could not have been more symbolically loaded. In 2015, a group at the Technical University of Denmark, led by Thomas Bohr, the grandson of Niels Bohr, ran their own double-slit experiment with walking droplets. They used 301 trajectories, 4 times as many as Kuda's original experiment. They found no clear interference pattern. The statistical distribution of scattering angles was essentially random. Bohr's grandson, challenging the pilot wave analogy. The irony writes itself. 3 independent groups attempted to reproduce Kuda's original result. None recovered the full quantum-like Fraunhofer diffraction pattern. Bush's MIT group, in a 2018 paper by Pucci and colleagues in the Journal of Fluid Mechanics, found that the droplet behavior depends strongly on the vibrational forcing parameters, and that 3 central peaks were visible in some parameter regimes, but the full quantum pattern was not recovered. The double slit result specifically remains contested, but the broader hydrodynamic pilot wave program survived this challenge and continues to produce striking results: quantized orbits, tunneling Zeeman splitting, corral statistics, spin states, Friedel oscillations published in Science Advances in 2020, superradiance published in Physical Review Letters in 2023, interaction-free measurement published in Physical Review A in 2203, and a hydrodynamic Aharonov-Bohm effect published as recently as December 2025. The double-slit result may be contested, but the broader demonstration that a classical particle wave system can reproduce a remarkable range of quantum-like behaviors is established. And experiments on actual quantum systems provided even more direct evidence. In 2011, Sasha Coxis and colleagues at the University of Toronto used a technique called weak measurement to reconstruct the average trajectories of individual photons passing through a double-slit interferometer. The trajectories they measured matched the predictions of Bohmian mechanics. The photon paths curved toward the center of the pattern, but never crossed the axis of symmetry between the two slits. This is a specific and distinctive prediction of Bohm's theory. In standard quantum mechanics, there are no trajectories to speak of. In Bohm's theory, the trajectories have a specific shape, and Coxis's group measured that shape. In 2016, Dylan Mahler and colleagues extended this to entangled photon pairs and showed that the so-called surrealistic trajectories objection raised by Englert, Scully, Sussman, and Wolfer in 1992 was not a problem with Bohm's theory, but a straightforward consequence of non-locality. Ephraim Steinberg, who led the Toronto group, put it perfectly. The disagreement arises not because Bohm's trajectories are surrealistic, he said. It arises because Einstein's spooky action at a distance is alive and well. So here is where we stand, a theory that solves wave-particle duality, that resolves the measurement problem, that produces identical experimental predictions to standard quantum mechanics. That has been confirmed by weak measurement experiments on single photons. That has been demonstrated in classical analog form on a tabletop with oil and a vibrating bath. That was proven mathematically equivalent in 1952. That was endorsed by John Bell, one of the most careful and insightful physicists of the 20th century. And that receives 0% support in surveys of professional physicists. 0. And if you think that number reflects a scientific judgment, if you think 0% means the theory was weighed and found wanting on its merits, then let me tell you one more story. Because what happened to David Bohm was not unique. It happened to someone else at the same time with a different theory, and the pattern was identical, which means it was not about pilot waves at all. It was about what happens when you try to take quantum mechanics seriously in a community that has built its entire culture around not doing so. And the human cost of that culture is something you are not prepared for. Hugh Everett III was born on November 11, 1930, in Washington, D.C. His father was a military officer. His parents divorced when he was young. By all accounts, he was brilliant, precocious, and deeply unconventional. He studied chemical engineering and then mathematics at the Catholic University of America, graduating in 1953 and arrived at Princeton for graduate school in physics that same autumn. His advisor was John Archibald Wheeler, one of the most creative and speculative physicists of his generation, the man who coined the term black hole. The idea came to Everett during a late-night discussion in 1954, reportedly fueled by what participants described as copious amounts of sherry. Everett started from a simple question. If quantum mechanics is universal, if it applies to everything, including observers and measurement devices, then what happens when you apply the Schrödinger equation to the entire universe? There is no external observer standing outside the universe to collapse the wave function. There is no classical measuring apparatus separate from the quantum system, because everything is part of the quantum system. So what happens? Everett's answer was radical and logically airtight. The wave function never collapses. There are no probabilities in the fundamental theory. What we call a measurement is simply the entanglement of the observer with the system being observed. When you measure a particle that is in a superposition of spin up and spin down, you do not collapse it into one or the other. Instead, the universal wave function branches. In one branch, you measure spin up and remember measuring spin up. In the other branch, you measure spin down and remember measuring spin down. Both branches are equally real. Both versions of you are equally real, and neither can communicate with or even detect the other. This is the relative state formulation, which Bryce DeWitt would later christen many worlds. Everett's original thesis was a long, detailed, mathematically rigorous document. It did not just wave hands about parallel universes. It provided the first rigorous derivation of the Bohr rule, the probability rule of quantum mechanics, from pure unitary evolution. It showed how the appearance of wave function collapse emerges from the entanglement of observer and system, without any actual collapse occurring. It addressed every objection that could be raised against a no-collapse interpretation. Wheeler was deeply impressed and called it one of the most significant ideas he had encountered. Wheeler took the thesis to Copenhagen. What happened there destroyed Everett's career and eventually his life. What happened in Copenhagen destroyed Everett's career. Alexander Stern dismissed the thesis as theology. Leon Rosenfeld, Bohr's most aggressive defender, was savage. He called Everett, and this is a direct quote that has been confirmed by multiple sources, undescribably stupid, and said Everett could not understand the simplest things in quantum mechanics. This from a man speaking about a mathematically rigorous work that derived the Bohr rule from pure unitary evolution and provided the first consistent account of measurement without collapse. Rosenfeld did not engage with the mathematics. He dismissed the person. Wheeler was sympathetic to Everett personally, but unwilling to challenge Bohr, who was his own mentor and the most influential physicist alive. Wheeler pushed Everett to cut the thesis to approximately 1/4 of its original length. The key arguments were compressed. The detailed derivations were removed. The shortened version was published in Reviews of Modern Physics in July 1957. It attracted almost no attention. In a discipline where being ignored is effectively the same as being refuted, Everett's thesis sank into instant obscurity. In 1959, Wheeler arranged for Everett to visit Bohr in Copenhagen to discuss the thesis. Everett later described the visit as hell and said it was doomed from the beginning. The 6 weeks he spent there produced no meeting of minds. Bohr was not interested in hearing that his interpretation was incomplete. Rosenfeld was openly hostile. Everett returned to the United States and left physics. Think about what that means for a moment. A brilliant young physicist working at one of the best departments in the world, under one of the most creative advisors in the field, produces a logically rigorous solution to the measurement problem, the central unsolved problem of the Copenhagen interpretation. And the response from the physics establishment is so hostile, so personally demeaning, so thoroughly dismissive that he abandons the discipline entirely and never publishes another physics paper. Everett took a job at the Pentagon's Weapons Systems Evaluation Group. His classified work included calculating fallout mortality rates for nuclear war scenarios, specifically the number of Americans who would die in various exchange scenarios with the Soviet Union. He programmed the first single integrated operating plan, which was the hydrogen bomb targeting list that the United States would execute in the event of a nuclear exchange. He founded defense contracting companies. He built an early Bayesian computing machine. He made money. He never set foot in a physics department again. He told colleagues he had washed his hands of the whole affair in 1956. The contrast between what Everett did with his life and what he could have done is almost unbearable to contemplate. He was, by every measure, one of the most original thinkers to come through Princeton's physics program. His thesis is now recognized as one of the foundational documents of modern quantum mechanics. It has generated an entire subfield. It appears in every serious textbook on quantum foundations, and its author spent his career calculating nuclear casualties and writing targeting algorithms for hydrogen bombs, because the professional physics community told him his ideas were worthless. Everett's personal decline was devastating. He became an alcoholic. 3 martini lunches were standard. He smoked 3 packs of cigarettes a day. He was chronically depressed. His son, Mark Oliver Everett, who would grow up to become the lead singer of the rock band Eels, recalled that his father never said a single word to him about his physics theories. Not once. Mark said later that he lived in the same house as his father for at least 18 years, but his father was a total stranger to him. He was in his own parallel universe. Everett died of a heart attack on July 19, 1982, at the age of 51. His son Mark discovered the body. He later described the experience in an interview for a BBC documentary. Feeling the cold body, Mark said, "I realized I had no memory of ever touching my dad before. That was the first time he touched his father, after his father was already dead." Everett had requested that his ashes be thrown in the garbage. His wife Nancy complied. Everett's daughter, Elizabeth, suffered from severe mental health issues for much of her adult life. She died by suicide in 1996, at the age of 39. Her suicide note read, "Please sprinkle me in some nice body of water or the garbage. Maybe that way I'll end up in the correct parallel universe to meet up with Daddy." I am telling you this not because it is about physics. I am telling you this because it is about what happens when a scientific institution decides that certain questions are not to be asked. Everett did not fail at physics. He was failed by physics. He produced a logically consistent, mathematically rigorous solution to the measurement problem. The problem that every interpretation of quantum mechanics must confront, and the professional response was personal ridicule, followed by total silence. He left the field, and the field lost 30 years of development of one of its most important ideas, and a family was destroyed in the process. And Everett's story matters here, because it proves that what happened to pilot wave theory was not unique. It was not about de Broglie's personality, or Bohm's politics, or the specific technical features of the pilot wave. It was about the institution. 2 completely different solutions to the measurement problem. 2 completely different physicists with different backgrounds, different countries, different political histories, different mathematical approaches. The same result: suppression, marginalization, silence. And in both cases, the suppression was maintained not by the discovery of a fatal flaw, but by social mechanisms: ridicule, omission, career pressure, the quiet agreement not to engage. There is a name for what happened to pilot wave theory and to many worlds. Historians of science call it the quantum muddle, a decades-long period in which the foundations of quantum mechanics were treated not as open scientific questions, but as settled philosophical matters that real physicists did not waste their time on. The quantum muddle lasted from roughly the early 1930s to the late 1980s, and during that time, working on quantum foundations was widely considered career suicide. Students who expressed interest in measurement, in interpretation, in what quantum mechanics meant rather than what it predicted, were warned by their advisors to drop it. Funding agencies would not support it. Journals were reluctant to publish it. Conference organizers did not invite people who worked on it. The result was a 50-year vacuum in which the most fundamental questions about the most successful physical theory in history went essentially unaddressed. The cost of this vacuum is incalculable. How many potential Bohms and Bells and Everetts were steered away from Foundation's work by well-meaning advisors who told them it was not real physics? How many graduate students had ideas about measurement or interpretation and were told that thinking about such things would end their careers? How many insights were never had because the people who might have had them were busy calculating scattering cross-sections instead? We will never know. But we know the vacuum existed, and we know who created it. Now, let me tell you what has been happening since the vacuum began to break. David Bohm spent his final decades at Birkbeck College, London, working with his longtime collaborator, Basil Hiley, to extend and develop the pilot wave theory. Their book, The Undivided Universe, was published in 1993, the year after Bohm's death. By the 1980s, Bohm had largely stopped presenting his interpretation at conferences. Hiley later recalled that Bohm was exhausted by it. He was tired of explaining that his approach was perfectly consistent, tired of answering ill-thought-out objections from people who had not seriously read his papers, tired of watching the objections get published anyway, tired of being ignored. In May of 1991, Bohm confessed to feeling suicidal and was admitted to the Maudsley Hospital in South London. He received 14 bilateral electroconvulsive therapy treatments over the course of several months. He was released on August 29, 1991. He showed improvement but suffered memory loss. He continued working with Hiley, but the intensity was diminished. On October 27, 1992, David Bohm spoke his last words. He said, "You know, it's tantalizing. I feel I'm on the edge of something." He died of a heart attack in a London taxi on the way home from Birkbeck College. He was 74 years old. He had been elected Fellow of the Royal Society only in 1990, 2 years before his death. A bittersweet recognition from an establishment that had spent 4 decades refusing to engage with his work. For years after Bohm's death and Bell's death and Everett's death, very little changed. The textbooks stayed the same. The curricula stayed the same. In 2013, Schlosshauer, Koffler, and Zeilinger conducted a survey at a Quantum Foundations conference published in Studies in History and Philosophy of Modern Physics, Volume 44, Number 3, pages 222 through 230. 33 physicists were polled. Copenhagen received 42%. Information-based approaches, including Cubism, received 24%. Many worlds received 18%. De Broglie-Bohm pilot wave theory received 0%. 0. Sean Carroll, the Caltech physicist and popular science writer, called this the most embarrassing graph in modern physics. And he was right, because what that graph measures is not scientific opinion. It is the fossil record of 90 years of institutional suppression. A more recent survey, published in Foundations of Science in 2000-2005, used a broader sample and found what the researchers described as a persistent preference for the Copenhagen interpretation, which they attributed to educational emphasis on the Copenhagen interpretation and its pragmatic appeal in avoiding complex metaphysical questions. Educational emphasis. That is a polite way of saying that the textbooks only teach one version, so the students only know one version, so the professors only teach one version, so the textbooks only include one version. The loop closes on itself, but something has been shifting, slowly, almost reluctantly, but noticeably. The 22 Nobel Prize in Physics, awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experiments on entanglement and Bell's inequalities, was a watershed. Not because of the specific experiments which had been performed decades earlier, but because of what the prize implicitly endorsed. The Nobel Committee was recognizing that asking foundational questions about quantum mechanics is legitimate science. That Bell's work, dismissed for decades as philosophy masquerading as physics, was in fact physics of the highest caliber. That the experiments testing whether reality is local or non-local, whether hidden variables can be ruled out, whether quantum mechanics is the complete story, these are real experiments answering real questions. This was the first time the institutional machinery of physics publicly acknowledged that foundations work matters. New textbooks have appeared that break the decades-long educational monopoly. Roderick Tomolka's Foundations of Quantum Mechanics, published by Springer in 2222, devotes substantial chapters to Bohmian mechanics, GRW spontaneous collapse theory, and many worlds interpretation, treating them as core subjects rather than historical footnotes. Duhr and Lazarevici's Understanding Quantum Mechanics, published in 2020, was described by reviewers as undoubtedly remarkable. A 2004 Springer volume called Advances in Pilot Wave Theory, part of the Boston Studies in the Philosophy and History of Science series, as Volume 344, collected the proceedings of the first international conference dedicated entirely to pilot wave theory, held in Lisbon in 2021. That volume includes previously unpublished notes by John Bell on de Broglie's pilot wave hypothesis, notes that have been sitting in an archive for decades, unread. The research community working on Bohmian mechanics is small but active and serious. Sheldon Goldstein, at Rutgers, who is the author of the Stanford Encyclopedia of Philosophy entry on Bohmian mechanics, has spent decades providing rigorous mathematical foundations for the theory. His correspondence with the Nobel laureate Steven Weinberg, published in the journal Inference, is remarkable. Goldstein methodically argued for Bohmian mechanics. Weinberg, one of the most distinguished physicists of the 20th century, conceded, "You are pretty persuasive." At MIT, John Bush continues the hydrodynamic analog research program. At Clemson University, Anthony Valentini pursues what may be the most radical implication of the theory. Valentini argues that pilot wave theory is not merely an interpretation of quantum mechanics. It is a deeper theory that predicts genuinely new physics beyond the standard framework. His key insight is the quantum non-equilibrium hypothesis. In standard quantum mechanics, particles are always distributed according to the Bohr rule. The probability of finding a particle at a given location is the square of the wave function at that location. Bohm's theory reproduces this, but only as a special case, as an equilibrium condition analogous to thermal equilibrium in classical statistical mechanics. Valentini asks, what happens if the equilibrium is broken? What if there exist, or once existed, conditions under which particles were not distributed according to the Bohr rule? The consequences would be extraordinary. Superluminal signaling would become possible. because the non-locality of the theory, which is hidden at equilibrium, would become observable and exploitable. The Heisenberg uncertainty principle would be violated, because the fundamental limit on joint measurements of position and momentum is a consequence of quantum equilibrium and does not apply outside it. Quantum cryptography, which relies on the impossibility of eavesdropping without disturbing a quantum state, would break down. Valentini believes that such non-equilibrium conditions may have existed in the early universe during the inflationary epoch when quantum fluctuations were amplified to cosmic scales. If so, they might have left detectable signatures in the cosmic microwave background, the faint radiation left over from the Big Bang. Collin and Valentini published a specific prediction in Physical Review D, Volume 92, in 2015. Lee Smolin has called Valentini the most important thinker of this century for defending the notion that science gives a complete description of physical processes. And the arrival time problem has emerged as a potential experimental discriminator between Bohmian mechanics and standard quantum mechanics in the laboratory, not just in cosmology. Das and Durr proposed in 2019 in a paper published in Scientific Reports that measuring the time it takes for spin 1/2 particles to arrive at a detector could reveal effects uniquely predicted by Bohmian mechanics, effects that depend on the particle's spin in a way that standard quantum mechanics does not predict. Scientific American described this as potentially the best test yet for Bohmian mechanics. The debate remains active. Goldstein, Tomulka, and Zanghi argued in a 2024 paper in Foundations of Physics that the relationship between detection time and arrival time is more subtle than Das and Durr assumed. The issue is unresolved. In 2005, David Darrow and John Bush at MIT published what may be the most significant theoretical result in the field in decades. They showed that a classical pilot wave system with genuine two-way coupling between particle and wave, the kind of coupling that Cuda's oil droplet walkers approximate, converges exactly to single-particle Bohmian mechanics in the appropriate quantum limit. This is the first rigorous mathematical demonstration that a classical pilot wave system can reproduce quantum mechanics, bridging the gap between the hydrodynamic analogues and the real quantum theory. The theory is not without genuine, acknowledged problems. Extending Bohmian mechanics to quantum field theory, which describes particle creation and annihilation and underlies the standard model of particle physics, remains incomplete. Progress has been made. Durr, Goldstein, Tomulka, and Zanghi have developed Bohmian approaches to quantum field theory that handle particle creation. But a fully satisfactory, empirically tested Bohmian version of the complete standard model does not yet exist. Sabine Hossenfelder, the German physicist and science communicator, has called this a game stopper. Whether it is a fundamental impossibility or a technical challenge that will eventually be solved is genuinely unknown, and I am not going to pretend otherwise. The honest position is that the non-relativistic theory is complete and equivalent. The relativistic extension is a work in progress, and the outcome remains to be seen. But that is not the point. Whether Bohmian mechanics turns out to be the final framework of physics is not the question that should trouble you. The question that should trouble you is why you had to watch a video on YouTube to learn that it exists at all, because the theory has existed since 1927. It was made rigorous in 1952. It makes identical predictions. It was published in Physical Review, the most prestigious physics journal in the world. It resolves the measurement problem. It eliminates wave-particle duality. It has been endorsed by John Bell, confirmed by weak measurement experiments, demonstrated in classical analog on a tabletop. And for 90 years, the professional physics community chose not to tell you about it. Not because it was wrong, not because it was refuted, not because experiments contradicted it, because Pauli was harsher than de Broglie, because von Neumann published a proof nobody checked, because Bohr controlled the institutions, because Bohm was a communist in the age of McCarthy, because textbooks copied other textbooks, because asking foundational questions could end your career, because the culture of shut up and calculate was easier to maintain than the culture of think carefully about what the equations mean, because the erasure, once it began, perpetuated itself through the feedback loop of education and hiring. Nobody learns it, nobody teaches it, nobody hires people who work on it, nobody learns it. You were told that wave-particle duality is a fundamental mystery of nature. It is not. It was solved. The solution was published, and then the solution was erased. Not violently, not officially, not by any single act that you could point to and call censorship, by the slow, quiet, grinding, devastatingly effective process of simply not mentioning it, not including it in the textbooks, not teaching it in the courses, not inviting its proponents to the conferences, and then, after enough time had passed, treating its absence as evidence that it was never worth mentioning in the first place. De Broglie saw the answer in 1927 and surrendered it because the room was hostile. He spent 25 years teaching physics he did not believe. Late in life, after seeing Bohm's work, he returned to pilot wave theory and spent his final decades working on it again. A quiet redemption that went almost unnoticed. Grete Hermann found the flaw in the proof that justified the suppression in 1935. She was ignored because she published in the wrong journal and had the wrong name and lived in the wrong time. The flaw she identified was rediscovered by Bell 31 years later, and only then did anyone care. Bohm rebuilt the theory from exile, proved the impossible, and was punished for it with organized professional silence that lasted the rest of his life. His final words were, "I feel I'm on the edge of something." He spent his entire career on that edge. The thing that kept him from reaching what lay beyond it was not physics. It was never physics. Bell proved the question mattered and died before the world acknowledged it. The Nobel Prize his work inspired was awarded 32 years after his death. Everett offered a different solution and was driven from the field by personal ridicule. His family was destroyed. His daughter's suicide note asked to be scattered into the correct parallel universe to meet her father. The question is not whether pilot wave theory is the final word on quantum mechanics. It might be. The arrival time experiments might confirm it. Valentini's cosmological signatures might be found. The relativistic extension might be completed. Or it might not. That question is open, and it should stay open, because open questions are what science is for. The question you need to sit with is what the erasure means, not what it means for physics, though it means a great deal for physics. What it means for you, for your relationship to the institutions you trust to tell you the truth about reality. Think about the chain of events. In 1927, a working theory was rejected at a conference because one man was rude and another was polite. In 1932, a proof was published that justified the rejection, and the proof was broken. In 1935, a woman found the flaw and was ignored. In 1952, a physicist in exile proved the proof wrong by constructing the thing the proof said could not be constructed, and the response from the most powerful figures in physics was to agree to ignore him. In 1964, another physicist proved that reality itself supports the kind of theory that had been suppressed, and his paper was literally lost in a drawer at a journal for a year. In 1990, that physicist died before the world acknowledged what he had done. In 2013, a survey found that the suppressed theory had achieved 0% support among professional physicists. That is not a story about one bad decision. That is not a story about one flawed proof or one hostile conference or one political persecution. That is a system that identified a challenge to the consensus and eliminated it through every available mechanism. Social pressure at Solvay, mathematical authority from von Neumann, institutional power from Copenhagen, political persecution from McCarthy, career incentives from the textbook and hiring pipeline, and the quiet, patient, grinding mechanism of omission, of simply never mentioning the alternative. The system worked. For 90 years it worked, and you are living in the world it created. Because every time someone tells you that quantum mechanics is fundamentally weird, that particles do not have positions until you look at them, that the act of observation changes reality, that Schrödinger's cat is simultaneously alive and dead, they are telling you the Copenhagen version, the version that was chosen by committee vote and enforced by institutional power. They are not telling you about the version where particles are always particles, waves are always waves. The cat is always alive or dead. Observation is just another physical interaction, and the apparent weirdness dissolves into a clear, deterministic, perfectly comprehensible physics. They are not telling you because they were not told. Their professors were not told. Their professors were not told. The last generation of physicists who could have told them were the ones who chose not to. In the years after 1952, when the alternative was published and available, and the community decided, collectively and explicitly, to ignore it. There is a postscript to Broglie's story that almost nobody knows. After Bohm's 1952 papers were published, de Broglie learned about them. He was electrified. Here was his own abandoned theory, the one he had given up on in 1928, rebuilt from scratch and made fully rigorous by a man he had never met. It worked. It had always worked. He had been right in 1927, and he had surrendered the right answer because the room was hostile. In the mid-1950s, de Broglie returned to pilot wave theory. He spent the remaining decades of his life working on it again, developing what he called the theory of the double solution, a more elaborate version that attempted to derive the wave function from deeper physics. He published papers and books. He organized research groups, but by then the damage was done. The physics community had spent a quarter century being trained that what de Broglie proposed was impossible. They were not interested in hearing from a 70-year-old aristocrat that the impossibility proof was wrong, and that his original theory had been right all along. His late work was politely received and quietly disregarded. He died on March 19th, 1987, at the age of 94. He had lived long enough to see himself proved right, and the physics community proved wrong, and it had not mattered. The textbooks did not change. The curricula did not change. If a complete, mathematically rigorous, experimentally equivalent answer to the most famous question in quantum mechanics could be erased from the scientific record for 90 years, maintained by a broken proof that nobody checked, enforced by career incentives that punished curiosity, and perpetuated by a textbook pipeline that selected for conformity over completeness. Then the obvious question is whether the same process is operating right now, on other questions, in other fields, with other answers that are sitting in journals, published and verified, waiting for someone to notice that the emperor has no clothes. Bohm said he felt on the edge of something. He was right. The edge he was on was not a scientific edge. It was the edge of a system that decides what counts as knowledge and what gets discarded. And the thing that should keep you up tonight is not that the system made a mistake. Mistakes can be corrected. The thing that should keep you up is that the system worked exactly as designed. It identified a threat to the consensus. It mobilized its authorities. It deployed its proofs and its textbooks and its career incentives and its social pressure. It neutralized the threat. It maintained its coherence. It did everything an institution is supposed to do, everything we rely on scientific institutions to do. And it was wrong for 90 years about the most basic question it is possible to ask about the physical world. What is actually happening when a particle passes through a pair of slits? The answer has been there since 1927. The particle is a particle. The wave is a wave. Both are real. Both exist simultaneously. The wave guides the particle. There is no collapse. There is no observer dependence. There is no mystery. There never was a mystery. There was only a choice, made by a handful of men at a hotel in Brussels, enforced by a broken proof that stood for 34 years, maintained by institutional power that crushed or exiled anyone who challenged it, perpetuated by a textbook pipeline that excluded the alternative so thoroughly that it ceased to exist in the culture, and sustained by the quiet, persistent, devastatingly effective refusal to mention that another answer existed. And you were never told, not because the answer was hidden behind a paywall or locked in a classified archive. It was published in physical review, in the open literature, available to anyone who looked. You were never told because the people whose job it was to tell you decided collectively and across generations that you did not need to know. They are still deciding